The following is a production of the University of Minnesota.
Basically, I'm talking about electric power as it relates to harnessing wind energy, and it's just the basic background that I'd like to present. I know that some of you are from civil engineering. How many of you are here from civil? Whoa, there are 10 registered, so but they're not here. Maybe they are on Unite. Are they on Unite? You think so? Okay, all right, that's okay. But so I'm not sure how to present all this material to people who haven't had any electrical engineering course. It's pretty challenging, okay? But we'll try. So anyway, electric power. Electric power is important. We all know that, right? And so as this slide shows, roughly 40% of all energy is first converted into electricity before we use it, okay, 40%. And here you see that in transportation, the difference of these two bars, 27.7 and 27.8, that's only 0.1, that is used as electricity. Because in this country, we don't have, electric railways and things like that, right? So very little is used as electricity. But if someday transportation also goes to electric, then it'll be a very large chunk. 60 to 70% of all the energy that we use would be in form of electricity. Okay, and what is quadrillion? That's like gazillion, right? Very big. So look that up. What quadrillion is? This is in BTUs. So these slides you have already through Moodle here. So here's power generation, electric power generation by fuel type. And this is somewhat old, 2008, but things have not changed all that much. And as you can see here, coal is the king here, right? About 50% is coal. And then you have nuclear about 20%, and then natural gas increasing. And then renewables, they are really right in the mud here, like 3.1% at that time, but may have gone up a little bit, 4 or 5%, but not much. But that's what needs to change, okay? I think climate change is a big issue. Whether human activity is contributing to climate change or not, that's like a religion. Either you believe in it or you don't, okay? But if you ask me what my religion is, I would say, yeah, it certainly is contributing. About 98% of all scientists believe that human activity is contributing to climate change, okay? Those who don't wish to believe, there's no way to persuade them, okay? But so I think using renewables in one way and another is a very important mission here. So what are the different types of options do we have? We have wind, on land, offshore. We have solar in the form of concentrated solar power, whereby these heliostats, fancy word for mirrors, you concentrate sun's rays on a tower, generate steam, and run a turbine, produce electricity. Or you can use it in the form of photovoltaic cells here, PVs. There's wave energy, there's geothermal, and perhaps you can throw in here a small hydro, okay? Big hydro, a lot of those potentials are already gone, and they cause a lot of disruptions. So a small hydro could be probably included here. So these are the different options we have. And many states have signed on to so-called RPS, Renewable Portfolio Standards. And you can see here states with RPS, they're in blue, and those, they have the goals, those are in yellow. So certainly Minnesota, as you can see, has a renewable portfolio standard, and you can go to this link and you can see in detail here. So you see here, target And state here, Minnesota, you see that Xcel Energy has a very aggressive target, 30% by 2020. So all the electricity supplied by our utility, Xcel Energy, by 2020 would be by renewables. Okay, and they are on their way to meeting that target. And and this will be out of this 30%, 25% would be from wind. Okay, so Xcel Energy, our local utility, is in nation's highest wind producer in a way. They may not produce it themselves. They may buy it from independent power producers, but then they sell it here. Okay, so that's Minnesota. And then what is eligible? You can see I'll not go through the list here, but if you look at Minnesota, and you can go down the list here, these are the different types of renewables that qualify under this RPS. Okay, and you can see the capacity growth. This has really slowed down. I mean, you can see that in 2011, there were large improvements, but 2012, I believe this is cumulative capacity, but we are, maybe just only first quarter is included here, I'm not sure, but it's somewhat looks like it's tapering off a little bit, okay? And the capacity by different states is shown here, and you can also see, so I'm not going to go through these slides, these are just for your information here, and these are the top states where wind is significant, and you can see here that we are over here, Minnesota, right here, okay? We used to be number 3, but now we are dropped down to what, number 5? 1, 2, 3, 4, 5, 6, number 6, yeah. Okay. Because some other states have, and in Minnesota, surprisingly, there is no addition in first quarter of 2012 here. This orange portion is missing here in Minnesota here, okay? One of the reasons I think we need to work hard to make wind more competitive is the pressure from gas. And you can see here in this slide here. So this is coming from DOE, our Department of Energy, and this is the estimate in 2016 here, okay? And you can see that conventional coal is slightly below 100 here. Wind here is slightly below 100, okay? Whereas if you look at gas here, so where is gas here? Right here. Conventional combined cycle, or advanced combined cycle here. It's about, about 70 or 65 or something like that. So that's really the pressure that you have because of this cost of electricity production from gas here. So, but I think there is possibility of improvements in wind. So let's look at this wind system. So about a few years ago, we had about 50 faculty from different states in summertime, and we all went to see a wind farm. It was a 100 megawatt wind farm. It had 41 Siemens turbines. Each was about 2.3 megawatt. Okay, so this was the nature of this wind farm, and so if you look at any of these wind farms, you have this turbine, the gearbox over here, and then a generator, fairly low voltage. So it was, in this voltage range, 690 volts was the maximum, and producing electricity at this variable frequency depending upon the wind speed. So faster it turns, higher would be the frequency. So, so generating this power of 2.3 megawatt at its rated condition and transferring it at this low voltage of 690, a lot of current has to come down here through this cable. So these cables have to carry under rated conditions as much as 2,000 or 2,500 amps. Okay, and then so at the base of each tower, there is this power electronics converter, and the role of this converter is to take this variable amplitude, variable frequency voltage and convert it to a constant amplitude and constant frequency voltage over here, 60 hertz. Okay, and then at the base of each tower, there is a fairly large 60 hertz transformer, which transforms this low 690 volts to 34.5 kV. So 34.5 kV was the collection voltage, and all 41 wind turbines were connected to this 34.5 kV network. And then there was a transformer which transformed this 34.5 kV to 161 kV, and that power was then carried on transmission lines to Xcel Energy System. Okay, so this was the structure, and a lot of companies now are putting this power electronics converter and this transformer on the top of this nacelle over here, so that the current that comes down is not so large. Because with this structure, these cables have to be very large to carry very large amount of current. Okay, so that is the reason why many companies now are putting the power electronics converter and the transformer on top of the nacelle. So does it make sense? Any questions? The structure here? Okay. Just to give you some information, GE's 1.5 megawatt turbine, they would supply this power production curve. So cut-in speed is about, let's say, 3 meters per second, and the conversion of meters per second to miles per hour is given here, and this rated speed is about 13 meters per second, and beyond which the speed of the turbine and the power production is leveled off. And at some point, there's a cutoff speed right here, perhaps, beyond which the blades feather, so the blades don't fly hard, okay, because of very high wind conditions, and the wind turbine shuts down. Okay, so that's really the way most wind turbines would work, regardless of the power rating. This happened to be a 1.5 megawatt wind turbine here. Yeah, right. They may be related to different tower heights. Okay, tower heights, because they sell these wind turbines with different towers. Okay, but you can certainly go to this website and you can check that out for sure. To be honest with you, I'm not absolutely sure what these 3 curves are, but I have a feeling they have to do with hub height here. Right. In this case, this hub height is given here, 64.7 meters here. Okay. Okay. So with this brief introduction, let's go into the electric power basics. This material we cover in 3 courses in roughly 120 lectures, okay, which we are trying to cover in 2 lectures here, basically. So this 2-hour slot that we have is equivalent to 2 lectures. So we'll talk about power systems, some basics, electric generators, and power electronics that is needed. And then if time remains, I'd like to talk to you a little bit about our research and also this curricular reform that we are carrying out here. Okay. And these are the references. So obviously you're not going to look at any of these books. But what I would recommend to you is that you go to this website here, listed here. And you will see many of these, 3 of these courses anyway, they are listed here. So how come, Marita, this, when I click here, oh, I see. Okay, let's not go there. Okay, yeah, you're right. Yeah. You go to that arrow type mode, right? It's like if you go here and this arrow here, then you can click here. And so here you can then see this website. And if you go to any of these courses, all the video clips for these courses are already uploaded, and you have access to them. Okay. So if let me just close this here. So these textbooks we use in our courses. For example, if I go back to this pen mode here, that's why I didn't want to do it. But let me see here. If I could go here to pen here. Okay, so for example, this one here we use in our advanced electric drives course 5705. This one for advanced power electronics 5741. This one in 4701. This one for power electronics. Some of you may be taking this course, power electronics, 4741. And this one from Professor Wallenberg teaches this course, 4701. So these all these textbooks we use. So let's look at this little bit of power system basics. All right, and then we'll look at power electronics converters and then also generators here. Okay. So if you, let's say, now we have to talk very basic here and you guys would laugh, but that's okay to laugh. So if you have a sinusoidal voltage source and if I apply a resistor to this, the current that will flow here, it's given by Ohm's law. So if I apply a sinusoidal voltage, this voltage here, voltage is given, this is the voltage here, and a sinusoidal current would flow, and this current would be in phase with this voltage, and this power that is being produced is, or being delivered, is the product of this voltage and this current here, right? And that power would pulsate as shown here by this dotted curve, and it has this average value here, this average power. So this average power is given by, see, I can't erase this here, but that's okay. Average power is given by the product of voltage and current here, where this voltage and current are designated by their RMS values, RMS, right? So if RMS voltage is equal to 1 over 2 pi, and you integrate from 0 to 2 pi, this instantaneous voltage times omega t. So this, maybe I should put omega over here. Plot is, omega is 2 pi times the frequency, okay? So that's this RMS value. And for sinusoidal voltages and currents, the peak value, which we may indicate by putting a hat on top, is equal to the square root of 2 times the RMS value. So this is RMS here. And this is the peak value here, okay, which you can see in these wave shapes here. All right. So now, if you have the same voltage and same current, but if this current is displaced from voltage, by this angle phi over here, as shown here. So you see you have two plots, voltage and current. And current is lagging behind the voltage waveform, in this case, by this angle phi. And if you multiply the voltage and current, the instantaneous power now is positive as well as negative. Okay, look at the dotted curve, right? So it's not as effective a way of transmitting. It's like you're moving forward and then you're moving one or two steps back and then you're moving forward again. Not a very good way, right? So that is what's happening here. And you can see for the same amplitude of voltage, same amplitude of current, the average power you have here is smaller than over here. So what happens is that in this case, the average power is given by the product of RMS voltage times RMS current, but there's another factor, cosine phi here. And this phi, in this case, was equal to 0. And therefore, cosine phi was equal to 1, right? So that's what happens when voltage and current are not in phase. And then we define something called reactive power, okay? So in these circuits, you can calculate them in time domain. So let's look at this circuit here. You have RLC circuit over here supplied by a voltage which is written in time domain. So I'm just trying to give you an impression here, okay? So can't go very much in detail. So if somebody gave me this voltage and I had to calculate this current, well, in order to calculate this current, I will have to write this equation over here. And I'll have to solve this differential equation. Well, I took my math course a long time ago. So it'll take me a while to solve it, okay? But I might be able to solve it. I'm joking, I probably will be able to. But the way we do it under sinusoidal conditions is that we make use of what is called phasors, okay? So, and we represent these phasors by putting a bar on top. So this is a phasor. Uppercase letter with a bar on top is a phasor, okay? So instead of writing it as in time domain, we write it as a phasor. Let's say this is reference, so it has 0 angle. And then these RLC, they become impedances. So R doesn't change, but this inductance, L, is represented as a reactance, J times omega L. Omega is 2 pi times F, okay? So, and similarly, this capacitor here is, minus J 1 over omega C, like this here, all right? So this impedance then of this RLC network is given by the sum of these three, and you can calculate the current that is going to flow here as this voltage phasor divided by this impedance Z, and this Z is a complex number which has an amplitude and has a phase angle, so this current here becomes I. Amplitude is given by this expression over here, and it lags behind this angle here. So once we know the current in the phasor, I shouldn't be pointing over there. When we know the current in this phasor form, we also know what it will be in a time domain. So how many of you have not seen phasors? Anybody from civil here? You have not seen it. You've not seen it, right? Okay. Well, now you have seen it. So it's kind of a trick. It doesn't have any physical meaning. You go through these motions and you come up with this way of doing it, and then you say, "Don't look back, just do it." Seriously, that's really the bottom line. Okay, so instead of calculating by solving a differential equation, you do it, it sort of becomes an algebraic equation, much easier to solve. We learn algebra in what grade do we learn that? Okay, so it becomes much easier. So, so the bottom line is that this voltage that you're applying and this current that is flowing, they are not always in phase. Okay, and there is a consequence of that, and that we call reactive power. Reactive power. Okay, so if, for example, in the circuit before, you apply this voltage and the resulting current is given over here, and you draw that as a phasor, then what will happen is the real power that flows from the subcircuit 1 to subcircuit 2, this real power is given by this here. Voltage times the current times cosine phi, and this current times cosine phi is really the projection of this current phasor onto this voltage axis over here, this I sub p over here. And then there is also a reactive power, Q. And this reactive power is given by this expression here, voltage times current times sine phi. And this current times sine phi is really the projection of this current phasor 90 degrees away from the voltage axis, this I sub q over here, right? And this reactive power is kind of a mysterious thing. Okay, some people describe it as like a foam on top of a glass of beer. Right? it's a really energy which is sloshing back and forth, okay, which is not doing any useful work. Right? Have you seen any better analogy of reactive power? You have seen it? What is it? I was asking if you've seen any better analogy. Yeah. Okay. So anyway. So what happens is that there's another quantity called power factor that is defined, which is really cosine of this phi over here. Okay. So when voltage and current waveforms are in phase, phi is equal to 0 and cosine phi is equal to 1. Okay. In that case, when cosine phi is equal to 1, this reactive power, as you can see, disappears, because sine phi would be, sine of 0 degrees is 0, right? So reactive power disappears. So that's the most efficient way to transmit power, by making the reactive power go to 0. But reactive power has its role, okay? And we'll talk about that. Then quite often when you go above a few kilowatt, we are always dealing with three-phase circuits, right? So here you see a balanced three-phase circuit, balanced voltages, and balanced load. And by balanced we mean is that these voltages are of equal amplitude, but they are displaced by 120 degrees from each other, okay, 120 degrees. So if I were to draw these balanced voltages, if this is the voltage for phase A, this will be the voltage for phase B, this will be the voltage for phase C here, something like this, okay? Not bad freehand. So, so that's what we mean by balanced three-phase voltages. And if these load impedances are the same as connected here in a Y connection shown here, then it is possible to calculate this circuit by just looking at, you can connect this point with this point over here by this hypothetical wire, okay? And in a balanced circuit, the current on that wire will be 0, okay? And therefore, at least in our imagination, we can connect these two neutrals, and then we can just calculate what current would flow because of this voltage. We can calculate this current just by looking at this three-phase circuit on a per phase basis, okay? And but we should also be aware of what happens to voltage from one line to the other line, VAB. And that is given by this phasor diagram. And you see that this line-to-line voltage is square root of 3 times the phase voltage. Okay? So if these are the phase voltages, VAB, VAN, VBN, and VCN, then line-to-line voltages like VAB would be here, VBC would be here, VCA would be here. Okay? And the meaning of VAB, actually I should write uppercase here. We're dealing in phasors here and put a bar on here. So VA minus VB here. Okay. Similarly, VBC would be VB minus VC here. Okay. And the power that is flowing in this three-phase from, let's say, from left to right, that we can write on a per phase basis. It will be given by this multiplied by 3. So that's because we have 3 phases. And then this voltage here, per phase voltage, is line to line divided by square root of 3. And you have this factor 3 over here, and you end up with this here. Okay. So you can compute this power, 3-phase power, in terms of line to line voltages times cosine phi. I should be able to delete all the alias all link on the slide here. Okay. Right here. Okay. So plenty to learn for civil engineers here. So I think these are the questions we make. These people should be able to answer, right? So we have to be careful. But please pay attention. So quite often we talk about things in per unit. Voltage is 1 per unit. What does that mean? That's just normalized. Okay? So you have some actual value, and you normalize it by some base value, and this becomes per unit value. So quite often you'll see in power systems, this per unit is used here. The other thing which is very important to recognize is power flow in AC systems. See, when you have DC, in DC, power flows downhill on voltage. So if I have a battery, okay, and a resistance over here, right? 2 batteries over here. Let's say this is 100 volts, this is 90 volts over here, right? Which way is the power flowing? From left to right, right? From 100 volts to 90 volts. Okay. So in DC circuits, power flows downhill on voltage. Whereas in AC circuits, it's really not the voltage amplitude. It's really the phase angle. So if you have a receiving end voltage over here, this voltage is here, and this voltage here is over here. So if this sending end volt, let's say this is side 1 and side 2. Side 1 and side 2 here. If side 1 is leading in phase angle, then power would flow from side 1 to side 2. Okay? That's how the power would flow, and how much that will flow is given by this expression over here. The amplitude product of these 2 voltages divided by the reactance you have in the middle, which is usually a transmission line, or it could be some inductance placed in series in this circuit, times sine of this angle delta, by which this voltage Vs is leading V sub R over here. Okay. So let me give you another example here. Let me go to erase all ink. Okay. If I had this VR over here and V sub S over here. So it's lagging behind V sub S. which way would the power flow in this circuit? It will flow from right to left. It will flow from V sub R to V sub S, because this angle between these two is negative now, as defined compared to this angle over here. Okay, so it doesn't depend upon the amplitude; it depends upon the phase angle, relative phase angle of these two voltages here. Okay, something very important to recognize. Okay, so any questions on this here? Anybody? No questions. Okay. All right. So this is just a diagram of power as a function of this relative angle between the two voltages, that it will be maximum when delta is equal to 90 degrees over here. Okay. Right. Now, in power systems, we always have transformers. Without transformers, it will be very difficult to transfer large amounts of power over long distances. So in conventional power systems, power is generated at fairly low voltage, like 22 kV, sometimes as high as 69 kV. But then there's a transformer which takes it to 500 kV, and then when you reach your destination or close to it, it may be transformed down to 115 or 230 kV, and then you may have another transformer which put it to a distribution level, 69 kV, and even further down to 4 kV, and then another transformer here which brings it to 120 volts or 220 volts, something like that. Yeah. Okay. So you can see that between generation and load, you have 1, 2, 3, 4, 5 transformers. So transformers are a good business to be in. Okay, you need lots of them. You have only one generator, but you have 5 transformers here, as you can see. And because you're transferring a large amount of power at low voltage, like the voltage at which is being generated, 22.5 kV, as shown here, you'll need very large conductors, right? And it'll be very costly. And the drop across them would be extremely large, things like that, right? So we need transformers. And these transformers work on Faraday's law, that this, if you have somehow this flux which is changing with time, then the voltage induced is N d phi dt here. Okay, so number of turns that you have in this coil and the rate of change of flux linking this coil would cause a voltage to be induced. So that's how these transformers work. And just to give you an idea what these power transformers look like, bigger than a bread box, right? And so this may be, maybe 100 MVA or 200 MVA transformer, okay? So all of us have seen transformers along the way, somewhere along the freeway, right? And so transformers usually have a primary and a secondary. And so as you can see here that here in this primary you have N1 number of turns, and in the secondary you have N2 number of turns, and the flux produced by these windings, it links each other, and there's a voltage transformation which is given by this turns ratio A, N2 over N1. So you can see that V2 is equal to is N2 over N1 times V1 here. Okay, so this is how we transform voltage from one level to another. Okay, voltage level. And similarly, something has to happen to current. So the current would be I2 would be equal to N1 over N2 times I1 here. or maybe I should put it this way here. Sorry, I should write this as I1 here is equal to N2 over N1 times I2 here. Okay. So if I apply a voltage V1, I'll get at the output this voltage V2 given by this turns ratio N2 over N1. And if I connect a load across here and this current I2 flows, then I1 would be given by this same turns ratio over here. Okay. Did I write it okay, Marita, here? Okay. Yeah. Because considering these transformers to be ideal, V1 times I1 is equal to V2 times I2. Okay? And you see that they all are consistent. Okay? But in power system, there could be a voltage collapse, and which is called voltage instability. And there are many ways to control it. One is by this reactive power. So reactive power is important. We talked about this fictitious thing where energy is sloshing back and forth, reactive power, but that is needed. And you can see here that, let's say you have a radial system. You have a generator here. You have a transmission line, and let's forget about the resistance of this line, just the inductance, and then you're connecting this load over here. So you can see that as you load more and more, and these curves are shown for different power factor. Okay, this one. I shouldn't be pointing. This green one is a power factor of 0.9 lagging. This blue one is power factor of unity, and this red one is a power factor of leading power factor. Okay, and you are increasing this power PR on the horizontal axis, and we are plotting the ratio of the receiving end voltage and the sending end voltage here, VR over VS. And let's say that starting it's equal to 1 over here at this point, and as we load more and more, the voltage at the receiving end is dropping. Let's say the sending end voltage VS we keep constant, 1 per unit here. Okay, and so as we load this line, the voltage is dropping, and how fast it drops depends upon the power factor. And remember, the power factor was defined as, it was, how was the power factor defined? Cosine phi. So it'll be, QR, no, I'm sorry. So this power factor is power divided by the apparent power. This is the power factor, PF. And apparent power would be, so PR over here, PR squared plus QR squared like this here. So that will be the power factor here. Okay, and that could be leading or lagging. Okay, depending upon in this load whether the current is leading the voltage or lagging the voltage. And so what happens to this amplitude of the receiving end voltage depends upon the power factor, as you can see from these 3 curves over here. Okay, but the bottom line is that beyond a certain point, this power factor, this curve reaches an instability, and so it's called a nose curve. This because the shape of this, and beyond a certain point, the voltage will run down to 0. Okay, and that's an unstable point. But so you really don't want to get anywhere close to that instability, and this can be somewhat prevented by controlling the reactive power. So, in the previous slide we talked about the effect of the power factor, and we can see here, if you apply Kirchhoff's voltage law, the bus voltage here is this Thevenin voltage, which is the voltage looking into the system, minus the drop across this reactance here. So that's this equation over here. But if you show it in terms of phasors, and let's say that you have a certain bus voltage here, this voltage bus right here, if the current that is drawn here is leading, as shown here, the sending end voltage is actually smaller than the voltage at this bus. But however, if the current that is drawn is lagging, like if you connect an inductor over here, it will be lagging. If you connect a capacitor, it will be leading. And you can see that in case when the current is lagging, the sending end voltage has to be larger than this bus voltage over here. Okay. So you can see the effect of current either leading or lagging over here. Okay. So it does make a difference. Okay. And so by controlling this, we can then control this whether we have lagging current or leading current. By controlling that, we can control the amplitude of this voltage here. So in power electronics, there is something called StatCom. We can come to that later, but it basically allows us to draw this current either to be leading or lagging. See, power electronics is like magic, okay? And you can, having this converter arrangement here, just a small capacitor, DC link capacitor here, this current that is drawn, this current could be made to be leading or lagging. So if I draw this V converter over here, like this current I converter could be over here, or it could be over here, like this here. And you can also control the amplitude of this current here. So it could be I could be here, or it could be over here, or it could be here, smaller or smaller here, like this here. So it's controllable, not only in amplitude, but also in phase. Okay, and that is called StatCom. And like I mentioned, the lagging current is associated with if I take this AC source, connect an inductor. This is the voltage. This is the current here. The voltage would be here. The current would be over here. Okay. Whereas if I take a capacitor over here, voltage, this current I, then if I draw voltage here, the current would be 90 degrees leading, like this here. Okay. So this power electronic device that we call StatCom, that can control whether you're drawing leading current or you're drawing lagging current, and therefore in one case you'll be drawing reactive power, other case you'll be supplying reactive power. And that makes a difference. That makes a difference in power factor, and therefore the voltage that we see, well, where did it go? Was it before transformers here? No, I think somewhere here. I had a nose curve here, right? Here, right here. Makes a difference. So in wind turbines, the way they are controlled, you can control the reactive power. Okay, you can control the reactive power. That's one good feature in these wind turbines. So, yeah.
Do they, the power generation companies, get paid
There is something called reactive power reserve. I'm not sure if they're paid to have that, but that's a good question. That's a good question. I'll check with Professor Wallenberg. You should check with Professor Wallenberg. I'm not sure if they actually get paid. But I know that you and I don't get charged for poor power factor. But large customers, they get charged by the utilities for poor power factor. Okay. That's for sure. But there are certain things, which are still under formulation, some policies. And so reactive power may be somewhere in that arena. Okay, so much for power systems. Okay, so now you guys are experts in power systems. So any questions on power systems? So what have you learned in power systems? So what have you learned in power systems? Well, first of all, we would like voltage and current to be in phase in most cases, a power factor to be unity, the angle between voltage and current waveform to be 0, right? That's unity power factor. So in most cases, that's the ideal way to transfer power, okay? And then so we looked at the definition of power factor. We looked at what RMS means, right? It's a way of defining voltages and currents. We looked at phasors. How do we represent them? And we looked at why we need transformers, okay, to convert from one voltage level to another, okay. And Manita, what else we looked at? We looked at the need for reactive power, and that reactive power can prevent, up to a certain point anyway, voltage collapse. Okay, so STATCOM can provide the reactive power. We also saw transfer from one AC source to another AC source, right? And the power flow in AC systems, you should remember that power flow in AC systems is downhill on angle. Unlike in DC systems, it's downhill on voltage, right? From 100 volts to 90 volts. Whereas in AC systems, from leading voltage to lagging voltage. Okay, leading voltage may be smaller in amplitude. Doesn't matter. Okay, it's the phase angle. Yeah.
As we increase the amount of renewables on the grid, does the amount of reactive power need to increase equally with that?
Well, as we, a lot of these systems can provide reactive power. Okay, reactive power. So that is, that is a requirement, or at least a very desirable feature of these converters, that they can provide reactive power. So that is true of wind turbines. Similarly, photovoltaic inverters can also supply reactive power. Okay, so they can in fact compensate for voltage drops by providing reactive power. Okay, so let's look at this topic that we are looking at now is power electronics here. So power from the wind, and it's given by this expression here. So this is the power in the wind itself here. So rho here is the air density, and then this is the area covered by the blades, and V sub W is wind speed here. And you can see that power in wind is highly nonlinear with wind velocity. It's to the cube, right? So you double the wind speed, the power in the wind would become 8 times. So this really is power in wind, okay? But what is available at the shaft of the turbine is this power times this coefficient of performance, CP, okay? And this CP here is shown in the graph on the right here for different pitch angles. So you can pitch this blade. So when you're catching all the wind, you're, at this theta equal to 0, which is the pitch angle here, are very close to 0, 1 degrees. And then you can start spilling this wind, and then this pitch angle becomes larger and larger, okay? And you can see that CP is decreasing. So you have this family of curves, but on the horizontal axis, so CP is being plotted here. So please pay attention to this curve here. And but at the horizontal axis, this lambda is, omega is the rotational speed. So this omega, sometimes people may say omega sub m, but it's really the rotational speed here, right here, divided by the wind speed, VW, over here. So it's ratio of the two, okay? And so these curves may be supplied by the turbine manufacturer, all right? And you can see that at certain value, this C sub p is optimum here. So let's say at lambda of 8, this C sub p is, what's the number here? What do you say? 0.48, okay? So this is, let's say, for this turbine, optimum value of C sub p is 0.48, and that occurs at lambda of 8. Okay? And theoretically, one can prove that it's about 0.59 or something like that. Okay? But practically, it's what you see over here when you're catching all the wind. Okay? And so what we have to do is, of course, we don't control the wind speed. So for any given wind speed, we want to control the rotational speed such that we are operating at this optimum value of lambda, which in this case happens to be 8. Right? So, it's very important that we control the rotational speed of this turbine. Okay, what control law it's used to get there? One of our presentations would talk about that. Professor Seiler would talk about that aspect. Okay, how do you control that? But all right. So these are the different types of interfaces one has. One is to connect this wind turbine directly to the utility using this induction generator. The other is to use what is called a doubly fed induction generator. So in this doubly fed induction generator, this is kind of old-fashioned. I don't think anybody is doing that anymore. But the other type, which is still widely used, is doubly fed induction generators, where in this induction generator, and we'll talk about that, the stator is directly connected to the grid. So here's the grid over here. Okay, so the stator, it may be connected to a transformer. We're not showing the transformer, but it's connected to the grid. But the rotor is a wound rotor machine, and you inject currents into the rotor through this power electronics arrangement over here. So you have AC on the grid side, you convert into DC across this capacitor, and from this DC, by chopping it up, you produce a low frequency AC and you supply currents through slip rings and brushes into this rotor. Okay, and so this is a doubly fed machine, and quite often used. And the advantage here is that most of the power that is generated flows directly from the stator to the grid without any power electronics. Whereas only, let's say, 10 or 15 or 20% flows through the rotor circuit. So power electronics is only 15 to 20% of the rated generation capacity of the machine. Okay, so that's and power electronics is still expensive. So this doubly fed induction machines are still used. The disadvantage is that you have only a limited range of speed in which you can control these generators, beyond which you'll exceed the rating of this power electronics too much, and then all the advantages would disappear. Okay, so so you're limited in speed over which you can control it, and the other disadvantage is that you have slip rings and brushes in the rotor circuit. There's a mechanical contact, not very desirable. Okay, so I think the future is really where you have this generator, whether it is a induction machine, and we'll talk about that, or it could be permanent magnet AC generator, and all the power is flowing through this power electronics interface here. Okay, so a great deal of new turbines are using this arrangement, and that Siemens wind turbine that I talked about, that figure I showed you earlier, that has this arrangement here. So this is a squirrel cage induction machine, and there is a power electronics converter which takes the variable frequency, variable voltage that is produced over here and converts it to fixed amplitude, fixed frequency voltage of the utility over here. Okay, and of course I'm not showing any transformer, right? So, but as you can see here, the entire power is flowing through this power electronics interface, whereas here only 15 to 20% is flowing through power electronics. Okay. The advantage, of course, here is that you can use there are no slip rings and brushes, and the other advantage is that you can control it over a very wide speed range. Okay, so that's really the advantage of these guys over here. And yeah.
Are permanent magnet machines on a big scale really common yet, or growing more common?
Yeah, they're becoming common. So if you look at GE's 1.5 megawatt, that is a doubly fed machine. If you go to 2.5 megawatt, that's a permanent magnet AC machine. If you go to 3.x, it would be 5 or 6 or something like that. That's again a doubly fed machine. But in between, you have permanent magnet. And what I didn't talk about here is that most land-based systems use gears. So propellers may be running at 15 or 18 RPM, but the generator may be running at 1800 RPM. It's geared up by a ratio of, by a factor of 100. But when you go to offshore wind turbines, the offshore wind turbines are much larger in size. So on-land wind turbines may be 2 or 3 megawatts a piece, right? But offshore wind turbines are more like 5, as high as 10 megawatts, because you have to build the platform. Think about building a platform offshore, right? So you don't want to spend all your money on building the platform and put a itty-bitty windmill on top of that. So you need a very big size windmill to justify that investment. And when you have such large power levels, 5 to 10 megawatts, gears become the biggest reliability issue. Okay, and so to eliminate gears, you have so-called direct drive. So your turbine may be running at 10 RPM, and so is the generator. So imagine your generator running at 10 RPM, very low speed, right? So at that, in that scenario, there's not much option but to use permanent magnets. Okay. So very large wind turbines use permanent magnet offshore. And as you know, the cost of permanent magnets is skyrocketing. Okay, so there's a big dilemma. So anyway, these wind turbines have to remain connected. It's called zero voltage right through. Even though the voltage, grid voltage may go down to zero, these wind turbines have to remain connected. I will not talk much about it. We'll have other speakers who will talk about it. So I think our purpose here really should be on power electronics. Okay, how do you go from variable amplitude, variable frequency to constant amplitude, constant voltage? So in between, we have this power electronics interface. So if this wind generator, this frequency here may vary from 10 hertz to, let's say, 60 hertz, right? Whereas here, this utility is always at 60 hertz, and this voltage may vary, let's say, 590 volts and down, depending upon the wind speed. So it's variable amplitude, variable frequency, and this is constant frequency, constant voltage. You can't connect the two directly, right? They're not going to like each other. So we need something called power electronics. And so what is this power electronics? Well, it's made up of solid state devices. So when we think of transistors, we think of very little devices, right? But we have very large devices, much larger than what you see here. They can handle several kilovolts and several kiloamps. So they can switch between off state to on state at such voltage and current levels. Okay. So really the advent of these solid state devices that has led to use of power electronics, and there are many types. So you have quite often in power electronics business, we talk about this device called IGBT, and this stands for insulated gate bipolar transistor, IGBT. Okay. So it has several advantages, and so by and large, all these wind turbines would use this device called IGBT. So insulated gate bipolar transistors here. Okay. So the bottom line is that they should operate as a switch, either fully on, fully off, right? So when a switch is fully on, it should have zero resistance. When it's fully off, well, it should have infinite resistance, right? Just like your light switch. And it should be able to go from off state to on state instantaneously, an ideal switch. Of course, these devices don't do that, but the hope is really to make them as ideal as possible here. So there are different frequencies and ratings which are shown over here. Some of the applications are shown over here. And so power electronics is being used, well, your cell phone has power electronic, your laptop computer, the supply that you have, that is power electronics based. And but they are used at thousands of megawatts at that power level, and several hundred kilovolts. So, so what do these power electronic interfaces do? So here you have, I said, 10 to 60 hertz, let's say, wind turbine, and here you have a 60 hertz over here. So one very common way to accomplish this is that you first convert this frequency voltage to a DC voltage across this capacitor. Okay? And once you have this DC voltage, you can chop it up to synthesize this 60 hertz. Okay? So you take DC, first you go from this variable frequency to DC, and then you chop it up and you convert it to the 60 hertz over here. So that's basically the nature of these things here. And just remember that what we talked about, how power flows from, so here is your E sub S over here, and this is the converter output over here, and there's some inductor in between here. By controlling the phase angle between the grid voltage Vs and this voltage being produced that you are producing by chopping this DC voltage, you can control the reactive power and real power. So P and Q, the reactive power here, they both can be controlled here. Okay, and similarly on this side as well. So that's how these power electronic converters work, and we have sort of a unique approach to describe this. So think of a switching power pole. Well, what is a switching power pole? It's a bipositional switch. Either it's in up position or down position. Okay, it has two positions, and you have a voltage port on this side, and you have a current port on this side here. Okay, and so let's look at what happens to this voltage here at the output of this switching power pole over here. You'll see that this voltage, and let's say that you are, making this switch go up and down with some high frequency, F sub S, which is 1 over this E sub S, switching time period here. So for a fraction of this switching time period, this switch is in the up position, and this voltage here is equal to this input voltage over here, right? Don't you think? When switch is in the up position, the voltage of this point A would be equal to this voltage here, right? What else could it be? And when the switch is in the down position, well, this voltage is 0. So you can see that this voltage is pulsating. The voltage waveform at this output of this switching power pole between Vn to 0, between Vn to 0 over here. Okay. This is all there is to know about power electronics. No, seriously. So you're going from one level to another level, and your load would not like that. So you put a filter. So you have an LC filter here, and you get, so LC filter, if you design it right, this switching waveform that is appearing, you can filter that out such a way that only the average value goes through and appears across this load here. So does that make sense? See, you are, by this switch, by making it go up and down very fast at the switching frequency, which may be, depending upon the size of the system, maybe let's say 50 kilohertz. 50 kilohertz. That means your switching time period is 20 microseconds. And you're making this switch go up and down, and we define the duty ratio D as the ratio of the time when the switch is in the up position, and T sub S here is the switching time period with which this waveform is repeating here. Okay, and so this duty ratio then determines what the waveform would be and what the average would be. So as you can see here, this average VA that appears, shown by this dotted line, is D times Vn. And this is a DC value which also goes through this LC filter and is equal to the output voltage VO here, right? So does this make sense? Right? So the bottom line is that you could go from 100 volts to 75 volts over here, or whatever, by properly controlling this duty ratio D, and this D is defined as the interval during which the switch is in the up position as a ratio of this switching frequency time period T sub S, right? Okay. So you can have the average anywhere between, so VO, which appears at the output here, would be between 0 and the input voltage Vn over here, anywhere in this range. Okay. So you can control that. And ideally, the efficiency would be 100%. If you had an ideal switch, which can go up and down at instantaneously and has no forward voltage drop when it's on, then where are the losses? If inductor is ideal, no resistance, okay, this whole conversion could be 100%, right? In reality, it's more like 95% or something like that, but it's much better than a linear regulator. Linear regulator is where you connect a resistance in series. And what does resistance do? Burn up power, right? I squared R loss. And so compared to so-called linear regulators, this one here may have very high efficiency, theoretically 100%. So this is what is called switch mode power electronics. So in that little power supply you have, or I have right here, this would be much bulkier if it was a linear regulator. But in here, in between, perhaps it's switching at, I'm just guessing, but like 300 kilohertz. Okay, the switches here, which are going up and down at 300 kilohertz. Okay, so that's really basically this principle here, right? Okay, so in this case, the power flow didn't work. Power flow is in this direction here. Power flow is in this direction over here. But through the switching power pole, it's entirely possible to make the power flow in the other direction. But let me just talk about how to realize this switching power pole. You may say, hey, this is what are you talking about is all fictitious. But to realize the switching power pole, what you have to do is take one transistor over here and a diode over here, right? So when we want to turn this switch in the up position, you gate this transistor like this here, and then this diode becomes reverse biased, and the current would flow like this here, okay? And when you want to turn the switch off, not off, but in the bottom position over here, you you turn this transistor off, this path disappears, and this current will circulate through here, and if this is an ideal diode, the voltage across here would be 0. Okay, so basically you have positioned this switch to the bottom. Okay, so by turning this transistor on and off, you can go from the switch being in the up position to down position. Does that make sense? Okay. So we can realize this switching power pole here. And we have a voltage on this side, and by having this inductor associated with the filter, we have a current port on the other side here. Okay, but this it is possible to transfer power the other way from a lower voltage to a higher voltage. So let's say Vn is here and Vo is over here. So Vo is greater than Vn here. You can boost up the voltage. Very hard. I mean, can you think of a linear circuit that will do that for you? Can you take 9 volts and can you produce 18 volts out of that, or 25? Not easy, right? So, but here you can do that. What you can do is you can, this is again a switching power pole. You can put a transistor here and a diode here in this case. So when you turn the transistor on, this switch is in the bottom position and the current would build up like this over here. Okay? And when you turn this transistor off, essentially the switch is in the top position over here and this current would flow into your output stage like this here. Okay. So in this case, the power flow is from this lower voltage to a higher voltage like this here. Okay. So depending upon how you structure this switching power pole, you can go this way or that way. Okay. From higher voltage to lower voltage, as we saw in a buck converter, or you can boost this voltage in the sense the power is flowing from lower voltage to a higher voltage. Okay. So that can be done, but in AC circuits where they will be used, the power can flow in either direction, this way or that way over here. Okay. And in order to accomplish that, we can connect these two in parallel. So this makes up the buck circuit which we saw earlier, and this makes up the boost over here. Okay, and these two transistors are gated by complementary signals, and basically here it's same thing is happening. It's going this way and that way over here, and you can make the power to flow in either direction. Okay, the power can flow this way, or power can flow this way over here. Okay. So that's what the nature of all these converters like. So, we saw that the waveforms that we get for example, the voltage over here is chopped up. But we're not really interested in chopped up voltage waveform. We want to filter that out, and that we will. So, but the better thing to do is to define it in terms of the average value on a cycle-by-cycle basis. So we put a bar on top. So lowercase voltage and a bar on top. So that's the average value. And you can see that this average value, which we saw in a buck converter earlier, same thing in boost, that is related to this DC side voltage by the duty ratio of this switch. And similarly, the current that is drawn over here, its average value is dictated by the duty ratio of this switch, or duty cycle. I use those, in the same sense, times this average value of this current over here. Okay. So it's given by this pair of equations, and that's very similar to a transformer. It's very similar to a transformer, right? So you can replace, on an average basis, this switching power pole by this transformer here. And this transformer has an adjustable duty ratio. Okay, when we had looked at the earlier power transformer, we had N1 over here and N2 over here, right? That power transformer. Whereas in this transformer, well, it's really not a transformer. You can't go to Radio Shack and buy this transformer. Okay, it's really made up of this switching power pole, but the average representation of a switching power pole shown here is by means of an ideal transformer with controllable turns ratio. See, in a real power transformer, not easy to control turns ratio, right? Whereas here, this duty ratio dA could be anywhere from 0 to 1. Okay. So it's an ideal transformer with controllable duty ratio, which is a representation of this switching power pole here. So what do you think, my friend? Does it make sense?
Sure.
Okay. No, I think we saw earlier that how this duty ratio controls the average value, right? And so that was done in a purely DC sense. But if you go cycle by cycle, you can also see that the average value is controlled by the duty ratio. Okay, and whatever happens to voltage transformation happens to current as well. Okay, so and so you have this pair of equations which are very similar to what you will see in a transformer. Okay, so why not just represent that by this, assuming that you have an ideal switch which has zero losses and so forth, by an ideal transformer as shown here, by and the turns ratio of this transformer is given by the duty ratio of the switch. And so don't forget that this really is a mathematical representation. Okay, for average values. And averages are what we are interested in. Recognizing that in a switching or switch mode power electronics, you have voltages which are jumping up and down. We saw that. Voltage going from Vn to 0 back to Vn, right? Vn could be 100 volts down to 0, back to 100, right? But on an average basis, so average is what we are really interested in. So that's what's shown here. That if you give me a DC voltage here, V sub D, and I want to synthesize here a voltage which is sinusoidal. Well, it cannot be sinusoidal starting from 0. Let's say I put a DC offset here, and on top of that, so here is 0, this is VD over here. I want to create this voltage waveform here. On an average basis. Okay? On an average basis. I should be able to create that voltage waveform. Okay, it cannot go above V sub D, the amplitude of this, and it cannot go below 0. But I should be able to create this voltage waveform, and if I look under a microscope at this instant of time, my voltage waveform here, VAN, may look like this here. Okay? And you can see here that I have a higher duty ratio here, T sub up. The duration which the switch is in the up position is longer, right? Whereas if I were to look over here, where the average is smaller, I see these pulses to be much smaller over here, right? This pulse here, as compared to this pulse over here. Okay. So by controlling the duty ratio of the switch, I should be able to synthesize this average waveform that you see here. Okay? Does that make sense? Right? So by constantly changing the duty ratio, I should be able to synthesize whatever I want here within a certain limit. I cannot get more than V sub D, and I cannot get less than 0. at this point over here. Okay. So the bottom line is that what we are trying to synthesize, let's say, is at 60 hertz. Just as an example, this average waveform, let's say, is varying at 60 hertz, and the switching frequency here, F sub s, may be, let's say, 50 kilohertz. So that's several orders of magnitude different than 60 hertz. Okay, and so these waveforms here, VAN, this waveform, for example, here, is constantly jumping up and down. This VAN is equal to V sub D down to 0, V sub D down to 0 here. Okay, but it's really the average of that waveform that at this instant of time has this value, and at this instant of time it has this value over here. But the actual waveform looks like this here. Okay, not very hard to appreciate, right? That by constantly changing this duty ratio, we should be able to synthesize this waveform. So what do you think, my friend? Right? Okay. So we are dealing with three-phase circuits. So we have, instead of one switching power pole, we have three switching power poles. Okay? And so instead of one, on an average basis, instead of one transformer, we have three, and we have three duty ratios, DA for switch A, D sub B for switch B, and D sub C for switch C over here. Okay, and by properly controlling these duty ratios, we should be able to synthesize three-phase AC voltage. So from a DC voltage source, I should be able to synthesize three-phase sinusoidal AC. Okay, so that's what these converters do. And if you apply that to a wind generator, what do we see here? That we have this variable frequency voltage here coming from the generator, and we have grid over here, and we have three switching power poles on this side, and converting this variable frequency, variable amplitude voltage to a DC voltage. And we have, again, three switching power poles, taking this DC voltage, chopping it up at some very high frequency, and then creating this AC voltages at these points in order to transfer P and Q over here. Okay? And by controlling the phase angle of the voltages that are generated here as compared to the grid voltages, we can control the real and reactive power. Right? Yes, sir. Rectifier? Rectifiers are they are old-fashioned technology. Okay, because using the rectifier, first of all, you cannot use rectifiers if you have induction machines over there, right? Because induction machines, as we'll see in 15 minutes, they require reactive power from the converter over here. Okay, so, and there are some other disadvantages. You cannot control the DC link voltage, which you can do over here. Okay. So most modern, I would say all, I shouldn't say all, most modern turbines use this arrangement here. Okay, where you have a switch mode converter on one side connected to the generator, and then you have another switch mode converter consisting of these three poles that you see on the grid side, and in between, across this capacitor, you have the DC bus voltage. Okay. And in this case, of course, the power flow is always in this direction, but also you can control the reactive power here by controlling the phase angles of these 3 voltages. And that's a very significant advantage for controlling the voltage in your wind farm. Okay. So you can generate these 3-phase AC voltages as you see here. Okay. And there are some other better ways to do it to get more out of your power electronics converter, but we will skip that. And same thing you need for photovoltaic. In photovoltaics, you have a DC bus over here, and this is AC over here, right? So you need some power electronics interface in between the two. Okay. So in 15 minutes, we had no breaks. It's supposed to be 100-minute lecture, right? Two class hours. But a little longer. So please bear with me, we'll be done. Generator. Okay, so we'll look at this part, and along with this power electronics here, this time here. So as you saw in so the role of electric drive is that you have a utility voltage over here, you have mechanical load, and you have a motor over here, and you can control the speed at which this motor turns. Okay? And power usually in an electric motor drive is flowing this way. For us, this is really not a load. This is a wind turbine over here, and the power is flowing this way here. But what's the difference, right? Power is bidirectional over here. Okay. All right. So how do these AC machines work? Well, there are 2 types of AC machines. One is called, well, there are more than that, but primarily 2 types that we use. One is induction machine. The other one is this PMAC, permanent magnet AC machine here. Sometimes it's called brushless because there are DC machines with brushes, right? So to contrast those, we call them brushless here. So there are 2 basic principles. One is that if you have a conductor carrying current in the presence of a magnetic field, there is a force on this here from, in this case, from right to left. And this force is given by the flux density, the current you have in this conductor, and the length of this conductor over here, okay, BIL. Okay. So that's a very basic principle. And the other is that if you take a conductor and you move it in the presence of magnetic field is in the plane of the paper, let's say, going in, and if you move it at some velocity u, there will be induced voltage, which is given by this flux density, the length of the conductor, and the speed at which this conductor is moving, right? Sorry, this is correct, my friend. You don't have to use your thumb. Thumb rule. But so the bottom line is that these are the 2 basic principles on which most of these AC machines work. And synchronous. This in my drawing here, it looks oval shaped here, but it's okay here, circular. But on the screen here. So, these machines consist of 3 phase windings. A winding in red, B, these are the magnetic axes of these 3 windings that are placed on these machines here. And let's say if you had a permanent magnet, north and south pole, and if you rotate them, these magnets, the voltages are being induced here. So my colleague, my mentor, Professor Riaz, sad news, unfortunately, he passed away just 10 days ago. So how come Anita, it doesn't work? Maybe it is working. Okay. So you see here. So you can click on these animations and play around if you have trouble sleeping. And you can see that as these this magnet on the rotor is rotating, these voltages are being induced. And these are 3 windings which are placed at 120 degrees to each other in space, and therefore the voltages that are being produced are displaced by 120 degrees with respect to each other. Okay, so that's a very basic principle of these machines. Okay, so I should go back to the pen mode over here, and the other thing is that when the currents are injected into these 3 windings, the field, the magnetic field that is produced is pulsating along each of these windings, but the resultant is rotating. So this is a very useful animation to see. So let me run this one here. Okay, so the magnetic field that is produced by these 3 windings is represented by these red, green, and blue arrows. Okay, but the resultant, as you can see, so these 3 fields are pulsating, right? You'll all agree. These arrows are becoming larger and smaller, right? But always along that a-axis. Look at this red arrow. It's always along a-axis, where it's becoming larger and smaller. But if you look at this resultant of the 3, it has a constant amplitude, and it's rotating what we call synchronous speed. And that synchronous speed is related to the frequency at which the currents, sinusoidal currents, are supplied to these 3 phase windings over here. Okay. So basically, these in machines you have magnetic field and you have conductors which are rotating, and therefore you have power and torque. So let's get rid of this here, and so we are back to this slide here. Let me go to the pen mode, and so we're not going to worry about how these windings are distributed, but the main thing is that when you have these currents, sinusoidal currents, IMA plotted over here, IMB and IMC, these are all displaced in time by 120 degrees. But if you look at the resultant field produced, it will be over here at time 0, at pi over 3 time, or omega t equal to pi over 3. It will be over here, it will be over here later. So it's synchronously rotating. And this will be rotating at omega sync, which is 2 pi times the frequency at which these currents are flowing here. Okay? So we're not going to worry about all this, but so how do permanent magnet AC machines work? I showed you the animation of that permanent magnet where permanent magnet was rotating inside a winding. So the same thing here. You have a north pole and you have a south pole on the rotor on PMAC machines, and then you have 3 windings which are placed on the stator. They are displaced in terms of their magnetic axis by 120 degrees, as you see here. And so this BR is really a space vector representing where the rotor field is. So north and south pole are like this. So the rotor field is like this here. Okay? And so in order to produce torque, what we need to do is to create a field from the stator such that it's at 90 degrees to this here. Okay? And so that is what is being done here. You can force the currents in phase A and B and C such that the resultant is 90 degrees to this B sub R. That becomes optimal. Okay? And if you did that, this will become a motor, and the stator is affixed to the foundation over here. It cannot go anywhere, and the rotor would then turn in this counterclockwise direction. Okay. If you want to make it a generator where you have an external prime mover, then you will make I sub s 90 degrees behind here, like this here. If IS was here, then this will become a generator. The bottom line is that we can seamlessly, in these machines, go from motoring mode to generator mode, but when it comes to wind application, it's always a generator, right? You don't want to make it a fan or something like that. So it's always a generator. So by controlling this I sub s, we can control how much torque is produced by this machine here. So PMAC machines are very easy to explain and understand once you understand these space vectors that I'm drawing. But the bottom line is that this B sub r is being produced by these permanent magnets, north and south pole, and it's rotating. And this I sub s is produced by IA, combination of IA, IB, and IC here. And the resultant, this IS, S stands for stator, you place that 90 degrees ahead if you want to, in the direction of rotation, if you want to make it into a motor, or you will have it 90 degrees behind B sub r if you want to have it operate as a generator. Okay, so that's how these PMAC machines work. When it comes to induction machines, in induction machines, you have the same three-phase winding, but the rotor is like a squirrel cage, You have bars along the periphery of the rotor, and these bars are short-circuited at both ends. So think of the rotor. We all have seen machines, right? So if you look at the rotor here, the bars are running along the periphery of this rotor. And then at both ends, they are short-circuited, what we call end rings. Okay, so it's almost like a squirrel cage, as shown in this slide over here. So how does this work? The bottom line is that, without going into a lot of details here in 2 minutes, that when you supply voltages and currents to these three windings, the magnetic field here is rotating in the air gap at the speed, let's say synchronous speed, related to the frequency at which you are supplying these currents IA and IB and IC. But the rotor itself is turning at a speed omega m, which is different. Okay? That means there is a slip between the two. We call it slip speed, right? So this slip speed is defined as omega sync minus omega sub m. Okay, and because of the slip speed, there are voltages induced in these rotor bars, and these rotor bars are short-circuited at both ends. So there are currents in these rotor bars, and therefore that force and torque that I talked about, BIL, right? That is produced. Okay, so that's how these induction machines work. And in a squirrel cage machine, you have to have omega m greater than omega sync in order to make it into a generator here. Okay, so let me just show you go through all this very quickly here. Show one animation here. And so, if you go to this animation and read up a little bit, you can see that in the motoring mode, the omega m is the rotor speed, and omega s is the synchronous speed at which this magnetic field established by the stator is rotating. And so omega m is less than omega s, but when you go to the generator mode, you'll see that omega m has to be greater than omega sub s. Synchronous speed. So very seamlessly, these machines can, as this torque's speed characteristic would show you, at this torque speed, will be done in a second here, okay? If you will bear with me. That this is the motoring mode, and this is the generator mode over here. And this is where the rotor is rotating at synchronous speed, but at speed higher than the synchronous speed, if this rotor is turning, then you go into the generator mode here, okay? So you can go seamlessly from the motoring mode to the generator mode. We are, of course, interested in the generator mode. By controlling the slip speed, you can control whether you're at this point, at this point, at this point over here, right, in terms of torque. You have different speed at which the rotor is rotating, and therefore you have different slip speed, and therefore different torques that are produced. So that's your torque speed characteristic. And then there's something called doubly fed induction machines, a little bit complicated to describe, but basically here we supply low frequency currents in the rotor, and they could be a generator when omega m is less than synchronous speed, or they could be a generator when omega m is greater than synchronous speed. Cannot do that with squirrel cage machine. In squirrel cage machine, omega m has to be greater than omega sync in order for it to be a generator. But in this case, it is possible in either mode, super synchronous mode or subsynchronous mode, to have it be a generator. Okay. So thank you very much for listening to all this. And so these are the references which you're not going to go to, but please go to this website if you will. Okay. And we will not talk about our research and all those things. So thank you.